In this video, we're going to continue our work on concavity and optimization. So now we're going to look at example 3, in which we want to find the critical values of our function and then use a graphing program to determine if those critical values are local extrema, that is, a local max or min. So when we are finding critical points, again, we want to find when the derivative is either 0 or undefined. So first step is we need to compute the derivative of our function. So our function is a quotient. So to compute the derivative of a quotient, we need to use the quotient rule. So I encourage you at this point to pause the video and try to compute the derivative on your own before moving on. And when you're ready, let's look at the problem together. So quotient rule tells us that to find the derivative of a quotient, like our function here, we need to take the derivative of the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. In other words, low d high minus high d low over low low. Just going to write that down. Low derivative of high minus high derivative of low over low squared. So let's set that up. So the denominator is 1 plus x squared minus the derivative of the numerator, which is derivative of 4x is just 4. Then we're going to subtract the numerator function, so 4x minus the derivative of 1 plus x squared. So the derivative there, derivative of 1 is just 0, derivative of x squared is 2x. Then our denominator would just be 1 plus x squared, all squared. So check your work on the first step of computing that derivative. And when you're ready, I suggest you combine or multiply out our terms here and try to simplify in the next step. And pause the video to do so. And when you're ready, let's look together. So what we can do here is multiply this 4 into each term, and then multiply out this 4x, 2x. So what do we get? We get 4 plus 4x squared minus 4 times 2 is 8. X times x is x squared, all over 1 plus x squared. So now are there any like terms that we can combine? Yep, we have a term 4x squared and 8x squared. So we can combine those like terms. And we are left with 4 minus 4x squared. And that's just because, again, we're taking that 4x squared minus 8x squared gives us a total of negative 4x squareds over 1 plus x squared, all squared. So now it's time to find the critical values by determining when this derivative f prime of x is undefined and when f prime of x is equal to 0. So first, undefined. Well, we do have a quotient for our derivative. So this quotient function will be undefined whenever that denominator is 0. Will that happen for us? Well, notice our denominator, we have an x squared term. So in order for 1 plus x squared to cancel out to be 0, this x squared must be negative. But whenever we square a number, we get a positive number. So there's no x values in the real numbers that we could plug in here to get a 0 denominator. So undefined, no. So now we just need to check when the derivative is equal to 0. So let's check when f prime of x is equal to 0. So that would mean 4 minus 4x squared over 1 plus x squared minus squared needs to be equal to 0. So that's only going to happen whenever this numerator is equal to 0. So that will tell us, therefore, that if that is the case, then 4 minus 4x squared is equal to 0. So now can you solve for what x must be here? All right, let's look together. So we can add the 4x squared over to the other side. So we get 4 must then equal 4x squared. Divide both sides by 4, and we get 1 must equal x squared. So that tells us we have two options for x, and that is x needs to be equal to plus or minus 1. So then our critical points, I can write here, critical points. When x is equal to -1 or +1. So now let's take a look at our graph to see what type of critical points these are. Do we have local extrema? So I head back over to my Desmos graphing calculator, and now I'm going to plug in my original function. Again, we use our original function to tell if we have minimum or maximum at those points. If we plugged in the derivatives, we just see that we'd have 0 or undefined at the critical points we found. So go ahead and follow along and type in the function on your own Desmos graphing calculator or graphing calculator. All right, so when you type that in, we should be getting a graph that looks something like this. And a cool graph here. And what I'd like us to do first is to identify where those critical points are. So we saw that critical points were here at -1 and 1. And we can see that yes, indeed, we have horizontal tangent lines there. And I'll just take it back to the next or the previous notes so that I can write some notes on here. So here is our graph. And again, I just want to highlight our critical points so we can see them clear here. And again, if we imagine the tangent lines, they would look horizontal like that. And so question is, okay, what do we have? Do we have local extrema at these points? Well, here at -1, our graph is decreasing, then increasing. So at -1 input, we do have a local min. So our graph doesn't get any lower or any smaller than the value output at -1 here. And over at 1, we see we have a local max. So we can say at x equals -1, there is a local min. At x equals +1, we have a local max. Awesome. Thanks for watching, everyone.